Hi everybody. So the next section we're going to look at here is section 9.3 on estimating a population standard deviation. So just to remind you, in 9.1 we looked at estimating a population proportion. In 9.2 we looked at estimating the population mean. So we'll sort of continue with what we're doing here, but here we'll be estimating a population standard deviation. And just like in the last section 9.2 we introduced the t-distribution, we will be introducing another distribution, in this case called the chi-squared distribution. As far as the objectives in this section, we will first of all want to find the critical values for the chi-squared distribution. And then, secondly, we will want to construct and interpret confidence intervals for the population variance and standard deviation. So remember, the variance is just the square of the standard deviation. So if you can find one, we can hopefully find the other ones. Maybe just to talk about the chi-squared distribution here a little bit too. So the chi-squared distribution is it's kind of like the t-distribution, I guess, but it's not symmetric. And the values for the chi-squared distribution will always be positive, whereas values for the t-distribution, if you remember, could be negative. And we'll see also that, sort of like the t-distribution, as the sample size increases, this chi-squared distribution, which we'll look at here in just a minute, it will become more and more normal. So let's look at the objective 1 and finding the critical values for the chi-squared distribution. Like I said, one thing that makes this a little bit more difficult is the chi-squared distribution is not symmetric, so you can't find the value on one side, and then if you need to find the value on the other side of the mean, you can't just double it like you did for the z and the t distribution. So a chi-squared distribution, then, if you have a simple random sample size n, is obtained again from a normally distributed population, so the underlying population has to be normally distributed, with a mean of mu and a standard deviation of sigma, then, and this will be our test statistic in this case, has a chi-squared distribution with n minus 1 degrees of freedom. And then, like I said, just like the t-distribution, the shape of this will depend on the degrees of freedom. So let's look at some characteristics of the chi-squared distribution. Some of these, which I mentioned already, is it's not symmetric. We'll look at the graph of it here in just a minute. The shape of the chi-squared distribution, again, depends on the degrees of freedom, just like the t-distribution. And as the number of degrees of freedom increases, the chi-squared distribution becomes more nearly symmetric, like I said, and then the values of the chi-squared are non-negative, greater than or equal to 0. And this symbol down here might look like an X, but this is technically the Greek letter chi, and so I guess they're using that for this statistic in this case. So here's what the chi-squared distribution looks for varying degrees of freedom. So this is with 2 degrees of freedom, it goes kind of like that, and then with 5 degrees of freedom, 10 degrees of freedom, 15 degrees of freedom, and then you can see that as x gets larger, as it gets closer and closer to 30, you can see that the distribution here becomes more and more like the normal distribution. But again, that's only for large sample sizes. So let's say, for example, that we want to find the chi-squared values that separate the middle 95% of the distribution from the 2.5% in each tail, and assume you have 18 degrees of freedom. So you would just go ahead and look at those values in your table. So there's a chi-squared table, I think it's table 7, or again you can use StatCrunch. But so 0.975 should give you, so remember this is the area, so that means that the distance here from the mean or the distance here from the mean will be 8.231 standard deviations, and the distance here will be 31.526 standard deviations, right? So again, you can see it's not symmetric, right? You have, you know, in the t distribution, if you went, say, 8.23 standard deviations, the area here would be the same as if you went 8.23 standard deviations to the right, but you can see that that's not the same in this case. Same for the z distribution. So objective 2 then would be to construct and interpret confidence intervals for the population variance and standard deviation. So the lower bound will be given by this formula, and the upper bound will be given by this formula, where alpha is the standard alpha we've used for, you know, alpha and or for the t and the z distributions. So let's look at an example. So let's look at some stocks, and so the following data represent the weekly return of for 15 randomly selected Microsoft stocks when we want to compute the 90% confidence interval for the risk of the Microsoft stock. Again, in this case, the normal probability plot and box plot indicate the data is approximately normal. Again, in most cases you will assume that, but you can assume that, but again, something you should really technically double check. The standard deviation, if you compute it, is given by this, so the variance would be just the square of that number. And then chi squared of 0.95 gives you 6.571. Chi squared of 0.05 gives you 23.865. And remember, this will be for 14 degrees of freedom because we had 15 stocks. So the lower bound then will be the degrees of freedom, right, times the variance, right, divided by your chi squared value. And then the upper bound, again, would be the same thing, except you would use this as your chi squared value, right, and that will give you those for the upper and lower bounds. So we're 90% confident that the population standard deviation rate of return for the stock is between 13.04 and 14.01, right? So that may not be a very good, you know, that's a pretty broad standard deviation there, or range there, but in this case, that's the best we can do, right? I mean, if you, I guess if you wanted a smaller confidence interval like 80, then you could maybe make that a little bit tighter. And then one thing to just be aware of is that you know, be careful whether you're looking for the standard deviation or the variance, right? So if you're looking for the standard deviation, in this case, then you might have to take the square root of some of the values here. So just something to be aware of. So if you guys have questions about any of that or anything, just let me know. So okay, so this is a fairly short section. Again, don't let the fact that the distribution is not symmetric sort of throw you off, or that we're throwing, you know, Greek symbols around like chi. You're just sticking into this test statistic and computing just like you did before. So I think that should wrap up that section. So if you guys have questions about anything else or anything, just let me know. All right. Bye.